All right, so we're going to consider this 4.6D. So it's the fourth video for 4.6 log integration. So this is just kind of showing like maybe it would be helpful for you to see a few of these. So look at what do you think here is the U? Let's just circle the U is going to be in red, okay? So if you look at this problem, the U is here. And it's a straight 3x squared is the derivative of this plus 1. So it's just a du, the derivative over the original, which is great. In this case, you would think that secant might be your u because it's to a power, it's on the inside, which is something I always talk about, but tangent's derivative is straight up secant squared. So that's your u. So this is our u, this is our u in this case. We get these other ones here, and if you kind of are focusing on just really the originals here, let's talk about what the u would be. Okay, so what would the u be in this situation? It looks like the u would be the bottom, right? X squared plus 2x. It does seem, and then your du is, right, 2x plus 2. And you don't really want those 2's in there, right? So if you just divide by 2 on both sides, you're going to get x plus 1, which is that, which is what you kind of wanted. So that's kind of the idea. So it's going to be ln of x squared plus 2, but there's going to be a 1/2. There's that 1/2 you can see from here, the du over 2. So hopefully that makes some sense. With this guy, what's the u going to be? Well, this is kind of clearer. U is equal to 3x plus 2. There's an extra constant in there because you know the derivative is 3, and there's no 3 here, but we can divide the 3. So there's going to be a 1/3 extra here. And you can kind of see how people could do these in their heads, like how my college professors make me do these kind of without doing the u substitution at all. They call it a hidden u substitution. Some people are probably able to get there. So if you have like, I don't know, 2x plus 5 to the 7th, right? And you're integrating that. Could you do a hidden u substitution? Well, I would say it's 2x plus 5, right, to the 8th divided by 8, right? And the chain rule is going to give me a 2 here, so there's going to be an extra 2 that probably would have been there. And that's pretty much my hidden u substitution. So I did a u substitution without really doing it, because that's the answer right there. So just recognizing forms is helpful. So let's do a little bit more. This is a change of variables with the log rule, so it just means it's like a little bit more annoying. I think it's really, actually if I go back, I wonder if this is that exact same example. 2x and then x plus 1 all squared. Yeah, so we kind of were doing this problem. So if you look back on the previous video, you might have tried this out a little bit. So let's just kind of see where we were at. We were right about, I think, well, I'll just work this problem. So keep in mind that I'm doing this example right here, example 6, change of variables with the log rule. It's the exact same one, and I'm just going to continue from here. So let's go through what I did, okay? So let's just kind of check it off as we go. So I picked the u to be the inside, and that, which, I mean, I was kind of torn here because they're both the same power, so I didn't know which one to choose there. But when in doubt, I usually choose the inside, so I chose the inside to be the u, and my du is decided to be dx automatically. So that's where I went. And then I went to the green here. So from there, I went down. We kind of talked about this a little bit. I put du here, which is dx, so that took care of that. I had u squared, which is this squared, so that took care of that. But there was this 2x, which I circled in blue, that I didn't know what to do with. And we've kind of dealt with this before. Well, then we came back here, and we said, okay, well, what is x equal? So what does x equal? X equals this. So what does 2x equal? Well, 2x equals this, right? So I took this, 2u minus 2, and I put it in for 2x. So I guess I had 2u minus 2 over u squared du, that integral. Now this integral looks a little ugly, maybe kind of tricky, but really we have to remember that that can be split into two fractions. Never forget that because that's an easily forgotten one. So it becomes the integral of 2u, so we're doing the opposite of a common denominator, minus 2 over u to the 2 over u to the 2 du. So I really have 2 the integral of u to the negative 1 du minus 2 the integral of u to the negative 2 du. I hope that you're comfortable with me making that change. And if you're not, think about it. Pause the video, just think about it for a few seconds. That's something we need to be able to do kind of fluidly as we move through the course. So this is then 2 ln of the absolute value of u, those are ln, minus 2, I guess that's going to be u to the negative 1/2 divided by negative 1/2. We're going to have a plus c here. So it's 2 ln of the absolute value of u plus 2 over u plus c. If you don't believe me, go ahead and take the derivative of that and see how it goes. Of course, we didn't put it back to x yet. So u is x plus 1. So it's going to be 2 ln of the absolute value of x plus 1 plus 2 over x plus 1 plus c. And if you think about it, we're really doing pretty complicated antiderivatives at this point, which is kind of nice. We're doing some things that are a little trickier. So that's where we're at. And let's see what we've got left. So that was this example, okay? So be aware that that was this example. Hopefully that's not confusing. And here's kind of like just a little quick discussion about this. Just guidelines for integration in general. You need to do these things. You got to learn the basic integration formulas. You need to know the antiderivative of du over u. You need to know what to do in the situation where you have the integral of secant squared, where you have the integral of those kind of things. You need to know what to do, okay? Find a formula that represents it, like find something that kind of works, and trial and error happens sometimes, okay? So try a u that will make it work if you're doing a u substitution. It's very typical that you're doing a u substitution. I'd say you might have more than half, maybe 75% of your problems are going to be u subs now. If you can't find one, try altering the integrand. So they talk about all the options. You have your sine squared plus cosine squared equals 1. Do some sort of trig identity, right? You could multiply and divide by the same quantity. We haven't done a lot of that, but you could do that. You could do long division. That's a good one. Or you could do two fractions, right? Instead of a common denominator, you could separate it into two different fractions and divide them. You know, negative exponents, think about negative exponents, making things into powers. Yeah, if you have computer software or your calculator, do that when possible. Okay, so now we're talking a little bit about differential equations. What is a differential equation? It's really just the same thing. Like, it's really just, think about it like dy equals 1 over x ln of x dx. So I move the dx over, right? Think of it like this. And then think of it like I'm just trying to find the integral of both of these. Well, what's the integral of dy? The integral of the derivative of y. So really what you think about when you see these is you don't get too afraid of them. You just realize that they want you to antiderive whatever's on the right, anything that's with that, right? And then they want you to, now that's really all they want you to do, right? I mean, that's pretty much it. So you kind of separate the y's onto the left, separate the x's onto the right, integrate both sides. Sometimes there's nasty stuff over here on the y side, but for now, it looks like you're staying free and clear of that. And I think that's really all we need to think about. So now we just need to go to this problem. Oops. Now we just need to go to this problem and see what we can do with it. So do you see a function and its derivative? This is a tricky one. So think about it for a minute. I see a function and its derivative. I see ln of x. What's the derivative of ln of x? The derivative of ln of x is 1 over x. So we want to pick our u to equal ln of x. Now, of course, you could have picked your u to be x ln of x, but then your du is going to have a product rule in it, and you're going to see pretty quickly that that didn't work. And then maybe you'll circle back and try this again. So if that's the case, then our du is 1 over x dx. Okay. And that means that we have y is equal to The integral of, we're still doing the integral. It looks like it's this 1 over x dx, I want to just let that be its own thing. That's all multiplied, so I'm just going to call that du, because that's what it is from here. And then I want to look at this right here, and I want to say, what's going on here? Well, this is actually the ln of x, but the ln of x is in the denominator, so it's actually 1 over u. So again, it's du over u in the integral. So ironically, there's some ln action going on here, because your u is an ln, but then it's an ln type of integration. So that can be weird. But your y is equal to ln of the absolute value of u, which I'm going to just go ahead and put it in as ln of x, plus c. Well, yeah, that's our u, right? It's the ln of the absolute value of u. And I just put it right back in. Should be able to derive this and get back to that original integrand. Okay? Strangely enough. And it will work. So that's kind of where we're at. Let's see what we got time for still. Hopefully we can at least talk about another one. So the tangent, how do we find the average value of a function? Well, the average value is going to be the area divided by the width. That's going to give you the average height. The height is equal to the area divided by the width, because area is equal to width times height. So if you divide the width, you're going to get height. Okay? So we want to find the area under tangent. Well, isn't the area under tangent just this? Don't we want the area under tangent of x? And then divide by the width of this region? Well, how far is this? This is a width of pi over 4. So we want to divide that by pi over 4. And we need to know what we're integrating from 0 to pi over 4, because that's the area that we want to go from that width. So we want to really just be able to do this problem. Okay? So I'm taking this example up a notch. And we are going to run out of time probably, so I'm going to kind of hurry here. I'm going to tell you that we have the integral from pi over 4 to 0 to pi over 4 of sine over cosine of x. Do you see a u substitution here that could work? We know we have divide by pi over 4, so I'm going to actually multiply by 4 over pi. Flip the right and multiply, right? Multiply by the reciprocal. Your u is going to be, I believe, sine of x. Now, I could be wrong. It actually might be cosine of x in this situation, but if the u of sine of x doesn't work, we can always try u of cosine of x, right? So actually, the more I'm thinking about it, I think your u is supposed to be cosine. So try u sub, try to solve this, and don't forget it's a definite integral. You got to plug things in. But we are pretty much out of time. We'll stop it there. As far as any other problems to try, I don't think so. Just be aware of other trig antiderivatives. Start thinking about those. Okay. See you in class.